Hey there, class. I wanted to give you a little video describing how we calculate a confidence interval and how we perform a hypothesis test. So in this video, I'm going to walk you through both of those calculations. So here's an example. Here's an example of calculating a confidence interval. So the average mathematics achievement score for a random sample of 100 sixth graders is 130 with the standard deviation of 10. And we want to calculate the 99% confidence interval for this mean. So let's start off with, what information do we know from this problem? We know the sample size is equal to 100. We know the sample mean is equal to 130. And we know the sample standard deviation is equal to 10. So those are all things that we can get out of the problem, and we're going to use this information then to calculate the confidence interval for this mean. So the first step in calculating the confidence interval is to determine the degrees of freedom. So in this case, the degrees of freedom are defined as 1 minus the sample size. So given our sample size of 100, the degrees of freedom in this case would be 100 minus 1, or 99. So then the next step, now that we know what the degrees of freedom are, is to look up what the critical value would be to calculate this confidence interval. So we can either use the critical value table that's on Canvas, we can use the critical value table that's in the back of our book, or we could use an online calculator that we basically give it the degrees of freedom and the 99% confidence interval, tell that that's the confidence interval we want, and it'll calculate the critical value for us. I've provided the link for that on the website. The link is also in the notes. The critical value in this case ends up being 2.626. Here's just a screenshot of the online calculator. Notice you type in the degrees of freedom. So we typed in 99 up there at the top. You select the confidence interval that you want. We wanted the 99% confidence interval. And then it prints out. You click calculate, and it gives you then the critical value for that confidence interval, 2.626. So we're going to use this information then to calculate the confidence interval. So basically then our next step, we have our degrees of freedom, we have our critical value, and we can basically fill in the formula for the confidence interval. So here's just a general form for a confidence interval. General form is a test statistic plus or minus a critical value times a standard error. So in this case, we're looking for the confidence interval for the mean. So we know the mean from our problem here is 130. We've looked up the critical value, 2.626. We have the standard deviation from our problem there is 10, and we have the sample size. So we can fill out all that information here. So, and basically then you just solve a little arithmetic here, and we'll solve this formula. Here I've walked through here. We can take the square root of 100 is 10. 10 divided by 10 is 1. 1 times 2.626 is 2.626. So 130 minus 2.626 is 127.4. And then 130 plus 2.626 is 132.6. So now we have our 99% confidence interval. So basically what this is telling us is we're 99% confident that the population mean for the mathematics achievement for sixth graders is somewhere in the range of 127.4 to 132.6. This is our best estimate of what then the population parameter may in fact be. So I hope that illustrates then how we calculate a confidence interval. For our next example, I'm going to walk through how to conduct a one-sample t-test. So let's look at our problem here. The average IQ score in the population is 100. Our team has developed a new drug that's supposed to increase intelligence. A sample of 49 participants who have taken the drug have a mean IQ score of 103 with a standard deviation of 14. We want to know whether our drug was effective in increasing intelligence. So the one sample t-test basically compares your sample mean with some known population parameter. So in this case, we've developed a new drug that's supposedly would increase someone's intelligence. We gave the drug to 49 participants, gave them an IQ test. Their mean IQ score was 103. We want to say, how likely is it then to obtain a sample of 49 participants with a mean score of 103, given that the population mean is 100. I mean, we wouldn't expect our random sample, the mean, to be exactly equal to the population mean. So how far off does it have to be before we can say that, yes, we think our drug is effective in increasing intelligence? So let's start off with what information do we know from this problem. We know the population average IQ score is 100. It's told us that. We know our sample size, which is 49. We sampled 49 people. We know their average IQ score after they've taken the drug is 103. And we know the sample standard deviation is 14. So we can use this information then to create our hypothesis test. So our first step is to state our hypothesis. So we're going to state then our null and our alternative hypotheses. So our null hypothesis is that the population mean equals 100, right? And we want to know, do we have evidence then in this sample to suggest that our drug is effective in increasing the average intelligence? So our alternative hypothesis is that the population mean is greater than, or you could say is not equal to, 100. So our next step is to compute the test statistic. Here I've given you the formula. So the general formula for our test statistic in this case is our test statistics will follow a t distribution. So it's a t-test since we don't know the population standard deviation. If we knew the population standard deviation, we could use a z-test, which the formula is basically the same. You just put in the population standard deviation here instead of the sample standard deviation. As we fill out our formula here, we have our sample mean minus the population mean divided by the standard error, which is the sample standard deviation divided by the square root of the sample size. So that's what I've begun to do right here. So we have 100 minus our population. I actually put this in wrong. We should be our sample mean minus the population mean, but it doesn't really matter. It's just going to flip the sign on us. Divided by our sample standard deviation divided by the square root of our sample size. There we go. The square root of 49 is 7. 14 divided by 7 is 2. 100 minus 103 is 3. 3 divided by 2 is 1.5. So that's our calculated test statistic is 1.5. So our next step then is to either look up a critical value or compute a p-value for our test statistic. If we're going to look up a critical value or calculate a p-value, We need to know what the degrees of freedom are for this test. And the degrees of freedom are defined by the sample size minus 1. So in this case, the degrees of freedom are 48. The t critical value ends up being 2.011, and I'll show you how we got that. And then our p-value is 0.142. We'll talk about how we get both of those. I calculated both of these using the online calculators. So this is the same one we used for our confidence interval, right? We type in the degrees of freedom. We're using an alpha of 0.05 according to the problem. So that corresponds to a 95% confidence interval. We click the little radio button on 95, click calculate, and we get our critical value, 2.011. We can get our p-value as well from a different calculator. Here we give the calculator our test statistic that we calculated, 1.5, and our degrees of freedom. So in this case, the p-value gives us then the probability of observing the difference we did, given that the null hypothesis is true. So what this is saying is, given a population mean of 100, how likely is it to observe a sample mean of size 103, a sample average of 103? And what this is saying, it's pretty likely it happens 14% of the time. So we're going to use this information then to make a decision about our null hypothesis. So we have a couple options here, and you can use either one. We can compare our critical value with our test statistic. In this case, for doing this, we want our test statistic to be larger than our critical value. Since our test statistic is smaller than our critical value, then we fail to reject the null hypothesis, or we don't reject the null hypothesis, right? Our test statistic didn't fall in the critical area of our sampling distribution. Basically what this is saying is that this is a pretty likely outcome to occur. And then the p-value is kind of getting at the exact same information. I think, in fact, it's 1402, so this is wrong in here. It should be 0.1402. But either way, so the p-value, what we do, if we use our p-value, we compare it to our alpha level. And what we want is our p-value to be smaller than our alpha level. In this case, since our p-value is larger than our alpha level, it's again an indication that we do not reject the null hypothesis. So in this case, what this is saying is that, well, really in both cases, what this is saying is that it's not a very unlikely outcome to occur. Like, it's not very unlikely to obtain a sample mean of 103, given that the population mean is 100. All right. If this was a very unlikely outcome, if our p-value was very small, say 0.001, then we would say, hey, that is a pretty unlikely outcome to occur, and we would reject the null hypothesis. Same thing as if our test statistic was really large. Say instead of getting a 1.5, we got a 3.9. Well, that's larger than our critical value. So we would say, hey, that's a pretty unlikely outcome to occur, given that the null hypothesis is true. So we're going to reject then that null hypothesis. This may be a little confusing right now, but as we work through more problems, we're going to use the same logic and decision making then throughout the semester as we move into two-sample t-test, as we move into analysis of variance, and we move into chi-square test. They're all going to use in the same logic, where we're going to compare either our p-value from our test with our alpha level. When you're running the analyses by hand, you either have to look up a critical value and compare it with your test statistic, or look up a p-value calculator. When you're using statistical software, it always gives you a p-value. It's going to calculate the actual probability value for you. And you're going to compare it with your alpha level. So our next step, we're going to compute a confidence interval again after we conduct a hypothesis test. We'll always calculate a confidence interval. We have the same form. We have our sample average plus or minus our critical value times our standard error again. We basically fill out this formula. The square root of 49 is 7. 14 divided by 7 is 2. 2 times 2.011 is 4.022. And then we have our confidence interval. So what this is saying is this would then be our best estimate of what the population average IQ score would be for someone who has taken our new drug. And notice that the population average of 100 falls within this range. So that's another indication that we are failing to reject then that null hypothesis. You know, this is saying that our average IQ score could be anywhere from, I don't know, 99 to 107. Is what this is showing us. Our final step then is to calculate an effect size. We'll always calculate an effect size with our hypothesis test, and the effect size is really try to speak to the practical or clinical significance of our findings. And so for this instance, we're going to calculate an effect size called Cohen's d. It's basically then the magnitude of difference between your sample mean and the population mean. It's taking the difference between the sample mean and the population mean and transforming it into standard deviation units, much like the z-scores we've talked about in previous modules. In this case, we do our sample mean minus our population mean, 103 minus 100 divided by the standard deviation. And we get a 0.21. So what this is saying is that our sample mean is 0.2 standard deviations larger than the population mean. Is that a large effect size? It all depends on the field of study. Cohen would classify that as a small effect, but a lot of times interpreting effect size is really dependent on one's field of study. What may be large in one field may be a small effect in another. I hope this was a nice illustration of calculating confidence intervals and hypothesis test. If you have any questions, please email me or post to the message board. Thank you.